The Big Bang is still the most widely supported hypothesis for the origin of the universe, but it isn't completely watertight. There are still some holes in the theory, problems with it, and mysteries that it doesn't quite solve. The true nature of the earliest particles, for example, those present right at the beginning of everything, is one such mystery. But science may well have finally found some answers. This is Unveiled, and today we're answering the extraordinary question, did one particle really save the universe?
Are you a fiend for facts? Are you constantly curious? Then why not subscribe to Unveiled for more clips like this one and ring the bell for more fascinating content?
Thanks to modern science, we know that if you zoom far enough into anything, you'll eventually get to a base level of fundamental particles, a microscopic plane of existence beyond which it's literally impossible to travel. It's a unique, shape-shifting head trip of a physical realm that now inspires many a sci-fi story or zany YouTube video. But it wasn't always this way, and we haven't always known quite so much about the subatomic world. Before the 1920s, the concept of the universe being constructed of fundamental particles at all was almost entirely unknown. Instead, most theories followed traditional thinking first set out by the ancient Greeks. The idea broadly went that the universe was built of continuously smaller chunks, and that if you were to cut into them, they would endlessly break down into infinitely smaller pieces. However, thanks to modern technology in the early decades of the 20th century, physicists such as Einstein, Planck, and Rutherford were finally able to go against this concept and provide an alternative. For the first time, it was shown that the universe does have a final fundamental level made up of tiny pieces called quanta, and also that the standard laws of physics didn't apply there. Instead, science established a new set of rules for dealing with this world of the very small, quantum mechanics. And this would later, in the 1970s, inspire the Standard Model of particle physics. The Standard Model says that everything in the universe is composed of only a few fundamental particles and 4 fundamental forces. It posits that by analyzing how these interact with each other, we can begin to understand how the universe really works. But the Standard Model is also a work in progress, and it too remains incomplete, which means that there are still some crucial existential questions that it struggles to provide answers for. The issue of matter, for instance, the stuff that makes up everything that we can see, still isn't entirely explained. Specifically, we don't yet know how it came to be here, how it came to dominate the universe. And now we're back to the beginning of everything, the Big Bang. When it comes to the Big Bang, what's known as the matter-antimatter asymmetry problem is a major issue. Most versions of the Big Bang theory say that the early universe should have had equal amounts of matter and antimatter, an equal number of particles and antiparticles, which are particles with opposite charge. Then, when the two opposites met, they should have annihilated each other, canceled each other out, leaving behind just energy. The earliest moments after the Big Bang should then, theoretically, have seen particles and antiparticles popping in and out of existence until all that was left was an empty void. That's what should have happened, but we know that it didn't. As is proven by the reality that is all around us, we know that ordinary matter somehow prevailed over antimatter. We know that a tiny percentage of ordinary matter didn't go through this annihilation process, that about 1 in 1 billion parts of it was able to survive. And that tiny amount eventually formed the building blocks of existence, of everything. The universe was born, and it quickly surged to become the amazing expanse that it is today. But scientists are still left scratching their heads over how and why it all happened. Thankfully, the head-scratching could soon be coming to an end, thanks in part to a 2021 study focusing on one of the fundamental building blocks of the universe, the charm meson, an extremely light subatomic particle. Also known as the D0 meson, the charm meson is one of just 4 particles cited within the Standard Model that can exist as though both particle and antiparticle at the same time. It does this via a phenomenon called quantum superposition, and as it moves between the two states, we say that it oscillates between the two. It's heavy science, but what does it all have to do with saving the universe? Well, in June of 2021, analysis of data from the Large Hadron Collider was published by a team of scientists from Oxford, Edinburgh, and Warwick universities. It specifically focused on the charm meson particle, recording millions of meson interactions triggered by the world's largest particle accelerator. Although we knew that charm mesons existed as both particle and antiparticle before this study, evidence of the oscillating transition backward and forward between the two had never been observed. This was largely because, as the study ultimately showed, charm mesons tend to decay too quickly compared to the time it takes for them to move between particle and antiparticle. One of the scientists leading the study, Professor Guy Wilkinson of Oxford University, explained as part of an official statement that, quote, "The oscillation is very slow and therefore extremely difficult to measure within the time it takes the meson to decay," end quote. Before reiterating that, quote, "The vast majority of particles will decay before they have a chance to oscillate," end quote. Nevertheless, this study managed to record charm mesons oscillating enough times to begin drawing some subatomic conclusions and inspiring some further lines of thought. Most significantly, the measurements taken seem to suggest that regardless of the speed at which charm mesons move between particle and antiparticle, they don't quite do so evenly. It could be then that there's a very slight alteration from the 50-50 split that science would usually expect, which, when we reverse all the way back to the moment of the Big Bang, could have been vital. It could be that charm mesons atypically produce more ordinary particles than antiparticles. That therefore, a tiny, tiny fraction of those ordinary particles were able to outlast their antiparticle partners, which then started to tip the cosmological balance in favor of ordinary matter. Because from the initial moments of the Big Bang, we know that gradually more and more ordinary particles were allowed to come into being, leading all the way up to the matter-rich universe we see all around us today. The stars and planets and creatures and comets. We know that they're all made of ordinary matter and not antimatter. But this observation of oscillating charm mesons could finally show us why that is. Importantly, the findings so far don't yet confirm that charm mesons really do settle as ordinary particles more frequently than they do as antiparticles. Proving or disproving that will be the next step for researchers. But still, we've arguably never been closer to understanding how the Big Bang played out, what the conditions were really like. Of course, science has grappled with the world's biggest questions for centuries, and history shows us how a steady stream of innovation, inventions, and genius theories have propelled us to where we are now. But it's only relatively recently that we've started looking for answers in the world of the very small. Traditionally, we've looked out at the stars in the sky, trying to make sense of it all, but now we're looking in. More than ever before, humankind is dialing down its existence to the most fundamental nuts and bolts possible, with particle physics ranking among the fastest-growing sectors in all of science. It's a difficult place of research, played out across a microscopic realm where almost all of the conventional rules of physics break down and refuse to work. And yet, we are beginning to get to grips with it. We are making progress. And this latest revelation, born out of the ongoing research at the Large Hadron Collider, is another tiny but mighty step toward a new enlightenment. Really, it doesn't get much larger or more all-encompassing than the actual universe itself, and we're still so far away from fully understanding it. But we now know that its secrets are tied up in subatomic packets, that it's guided by forces and particles we cannot see, and that it's shaped and was maybe even started by them as well. And that's why this one particle, the charm meson, really might have saved the universe.
What do you think? Is there anything we missed? Let us know in the comments, check out these other clips from Unveiled, and make sure you subscribe and ring the bell for our latest content.